Welcome to the first session today and about security proofs. So we have three talks today, and the first talk is about treating dishonest ciphertext in post-quantum KEM. And Mikhail Kudinov will present for us.
Thank you for the introduction. So, in this talk, we will be looking at key encapsulation mechanisms and the way to build them, and a special part of it is the ways to reject bad ciphertexts. This is a joint work with Katrin Hovelmans. So, what is our aim? Our aim is to get the key encapsulation mechanism, and one of the most common approaches is to apply Fujisaki-Okamoto transform to a public key encryption scheme. This is a general transformation that is applied to a big set of different public encryption schemes. You use some hash functions to de-randomize the encryption, and the hash function to derive a key. We will look at it at more details a little bit later. And yeah, for example, one of the schemes that use this approach is Kyber, which is now a new standard. So let's look a little bit in more details. Our goal is to derive a symmetric key for future communications. And to do this, you can take a public key encryption scheme, you take a hash function, and what you do, you sample a random message, you encrypt it, you send it over, and use a hash function to derive the key. The receiver obviously decrypts and also can derive the key using the same hash function. But what is the security model we're looking at? We want chosen ciphertext security. So what are the capabilities there? We run an encapsulation mechanism. We get a key, we get a ciphertext. We also sample a random key, and then the adversary gets the ciphertext and either the random key or the one derived from the honest run of the encapsulation algorithms, and then the adversary has to distinguish these two cases. The problem is that the adversary in the CCA model also gets the decapsulation oracle. He can ask for decapsulation queries, he can submit the different ciphertexts. We exclude the possibility, obviously, to submit the challenger ciphertext, but the problem is that the adversary can generate those ciphertexts not dishonestly. He can run a different algorithm or try to manipulate some ciphertext, switch some bits, or do different things. And those ciphertexts can be generated not from an honest run. And what we want to do, we want to detect such malicious, such dishonest ciphertext and punish them by rejecting and not giving the key for such queries. To do so, we apply Fujisaki-Okamoto transform. So we take a randomized public key encryption scheme. This is important. The results of this talk will apply only to randomized public key encryption schemes. And a randomized public encryption scheme takes the public key, the message, and some randomness, and produce you a ciphertext for that randomness. And the idea is to derive that randomness with a hash function. You hash the message, you get the randomness, you encrypt in this way deterministically, and you also derive the key, but you use a different hash function to derive the key and a different one to derive the randomness. And then we modify the decapsulation algorithm. We receive the ciphertext, we first decrypt it, get some message out of the decryption, and then we run a re-encryption check. We perform again the encryption and compare the results, if we get the same ciphertext or not. We hash the message, get the randomness, encrypt. If there is a mismatch, we reject. If everything works out, then we return the key. And the idea is that if we run, for example, if I generate a ciphertext with a different randomness, not from a hash function, then I will get different ciphertext, there will be a mismatch. If I just choose a random bit string and assume this is a ciphertext, there is a high chance that it will it would have been generated using just random strings and not the randomness, the one that we would use with a hash function. So this way, we will be able to detect most of malicious ciphertext. But the question is, reject. How do we reject? There are two mainstream, there are two possible scenarios what you can do. You can either reject out loud, give a special symbol, you say, yes, this is a rejection, you submitted dishonest, bad ciphertext, or you can try to hide that you reject, and you return a random key. Completely unrelated to the ciphertext you get, this will not work for the communication, but from the outside, it will be hard to tell in which branch we are. Did I submit a good ciphertext or not? I anyways get some bit strings, and for me, from the outsider, it's hard to distinguish what happened. How these two differ? The intuition that maybe implicit rejection gives us more security because we give less information to the adversary. Maybe because he doesn't know that we're rejecting, it will be harder for him to attack the scheme. And the history kind of went like this, that the proofs for the implicit rejections were available much earlier. And during the first rounds of NIST standardization process, there was only a proof for implicit rejection. And so I think most of the submissions used implicit because of that. Then the explicit rejection proof was developed, but the first proof for explicit rejection required a modification. You needed to send extra information besides the ciphertext. You needed to send a key confirmation hash, and that worsened the scheme a little bit. Then the proofs developed more, and we actually got proof for explicit rejection without these modifications. But that proof was less tight than for the implicit rejection. And finally, in 2022, there was a paper that showed that we can get almost pretty much the same security guarantees for explicit rejection, the same as implicit rejection. But the problem, the thing is, okay, we have a proof for implicit rejection, which gives us certain bounds. We have a proof for explicit rejection that gives us certain bounds. Are they different? Of course, if you have an explicit rejection scheme and you think it is secure, you can also substitute your explicit rejections with implicit ones. Because you pretty much run the explicit scheme, you transfer the queries from the adversary, and when you get the rejections, instead of sending the rejections to the adversary, you just send random strings, and pretty much this way you get the proof. But the other direction is harder. And in our work, we actually managed to show that explicit rejection is also essentially as secure as implicit rejection. That you also can reduce attacks for explicit and implicit schemes. They will be interchangeable. The restriction, though, is important. Is yes, our result only applies for the key encapsulation mechanisms that are built from randomized public key encryption scheme through this modification. In general, there are schemes that do not apply F4, and then for that, the result doesn't apply. And so the idea of the proof, one more thing to say here is that the result in the quantum random oracle model with an extra interface. There is we modify a little bit the model, and this is not super standard, but these modifications is small, and we show that for the adversary doesn't change the view. Almost anything changes, and so but these modifications, as I will show in a few following slides, help us to get the proof. So first, let's look if we model the hash function as classical random oracle to get the intuition. In the classical scenario, we model our hash function that is used to derive the randomness as a random oracle, and you can implement the random oracle just as lazy sampling. You get queries, message 1, message 2. For each query, you generate a random output, and you store the queries in the list, which you can look through. And if you get repeating queries, you use your previous answers. If you get new queries, you get you generate new randomness. And the idea is that if you run an honest encapsulation run, you have to pick a message, and then you have to query the hash function. So for every honest run of the algorithm, there will be a record in the random oracle database of the message and the corresponding randomness. And to answer the decapsulation queries, you don't actually need to know the secret key. You can just look at those queries and check. If there is a pair message with randomness, if you encrypt this pair, do you get the ciphertext that is asked to decapsulate? If there is such one, you say, OK, then let's return the key using this message. If there is no such pair, you can assume that this is a malicious ciphertext. There are some restrictions. Your scheme must be spread, which means like for different randomness, you get a different ciphertext, so it's hard to predict which ciphertext to use. And you can also like try to find failing plaintext collisions like this. If your encryption scheme is not 100% correct, there is a chance that, for example, you can have same ciphertext for two different messages, even for an honest run. So if you can find such things, you also can distinguish this. But all of this has negligible probability for the interesting schemes that we're looking at. To move to quantum random oracle model, we have this extra interface which is called the extraction interface, and this allows us essentially for the same capabilities. For the classical sense, we could actually look at the records. The extraction interface gives us an ability to query, hey, is there a record in your database that if you encrypt this message and randomness, you get this ciphertext T? So yeah, here you submit the ciphertext, and yeah, the QROM gives you an answer if there is such an input, and if there is, it will return it to you. If there is no, you will not get an answer. So this allows us to lift the proof to the quantum random oracle setting. Here we don't have the database anymore, but we can use the extraction interface on this side to perform the similar checks. And so, yeah, this way we were able to show that explicit rejection and implicit rejection are essentially equivalent. But here the question is, what should I use? And arguably, the implicit rejection is very hard to keep it in real life. Because when you run your key encapsulation mechanism, you will run it in the protocols, and the outside protocols probably will reveal if the key that was derived during this run is a good one or it is a bad one. Because if it is a bad one, you will not be able to communicate and the connection will drop. And so from the outside perspective, it will be possible to see that a rejection happened. And for implicit rejection, it is important to hide those branches. And so arguably, you should rely on explicit rejection proofs. But as we saw, if the scheme is secure in the explicit sense, it is also secure in implicit one. And so you should rely maybe your security on the explicit rejection, and then in practice you can use it implicit. Yeah, thank you.
So any question for Mikhail? Yes, please.
Thank you. It's a very useful result. Thank you for that. So a little bit related, I'm curious, I was looking at HQC recently, and the document, which is fairly recent, actually says that it's using the 2017 implicit HHK result that MLKEM does, but then I noticed that it's actually doing something a little bit different. It has this salt parameter. So then I was looking a little bit further, and I realized that perhaps the authors are using, perhaps you guys have been in loop in that thing, because there's been a recent paper by Catherine and I believe yourself where no.
I wasn't involved in that paper.
Okay.
Yeah, I'm not sure about the HHQ scheme. Yeah.
Okay, so all right, thank you.
Yeah, sorry.
It's of practical relevance now.
Yeah.
Other questions? So maybe I can guess one. You mentioned about the modification for this content randomness oracle, right? And do you know or have you checked how different? I mean, to classical random content model.
In terms of like the modification that we add?
Yes,
or,
yes.
So we also, this modification give the adversary a little bit more capabilities, but in the paper we also show like with these extra capabilities, the old proofs all remain the same, and like if the adversary gets these extra capabilities and try to attack our implicit or explicit schemes, the same proof goes through, so you get the same bounce. So these capabilities doesn't give. Okay, there is a factor of 2 there, but this is
okay, so
pretty much the same.
Not much difference.
Yeah.
Okay. Other questions? So if not, so let's thank Mikhail again. Thank you.
Thank you.